All right, let's continue by looking at a third example. As you can see already, this is an interesting problem because we are dividing by x squared. We've been working with well-behaved functions, functions that are continuous on all real numbers, but as you can clearly see here, this function is not continuous on all real numbers. As a matter of fact, the domain would be all real numbers except for where x equals 0. Okay. So when we look at this, when x is 0, the function evaluated to 0 would give us 3 over 0. So we, in fact, do know that that's a vertical asymptote. I might suggest that right now, because this function is different and you notice that the domain is not all real numbers, this might be a good time to kind of come over here and get started building your f prime number line. That way, on the number line, you need to consider that when x is 0, we have a vertical asymptote because we did some investigation over here. And I want you to think about that because a function at its vertical asymptote could change directions, meaning on either side of the vertical asymptote, the function may change directions. So that's something important to kind of put on the f prime number line so that we're looking at appropriate intervals, breaks in the graph where the function may change direction. Okay, so that's why I didn't build the f prime number line first in the previous example because the domain was all real numbers. There wasn't anything interesting to consider. There were no breaks in the graph. All right, let's come back over here. We know what the objective is. It's to find the derivative. Okay, well, you might want to go back and practice the quotient rule. Okay, I think that would be a great idea. But what I'm going to do here is I'm just going to give you guys the derivative. I encourage you maybe to pause the video and go, you know what? I don't really remember the quotient rule. Okay, let me go ahead and practice that somewhere and see if I end up with this result after the cleanup. Okay. Notice here also I could factor out an x. I left that in there, but notice now I could factor out an x and cancel it with one of the ones in the denominator. So in fact, I end up with negative x minus 6 over x cubed. For the purposes of what we're doing, it's not real critical to simplify all the way down, but it does help with your work. All right, so let's take a look at this derivative. We want to consider critical numbers. So 1, let's go ahead and take care of the issue of where does the derivative not exist. Well, clearly we can see from this fraction that when x is 0 in the denominator, okay, the derivative would not exist. But remember that when x is 0, we already have that the function is not defined at 0. So we can't really say that there's a critical number that's occurring at x equals 0 because there's not even a point there in the graph. If you need to, you might want to stop, pause, rewind, think about what I just said, or just process that there's no way to have a critical number if there's not even a point there. The function itself didn't even exist at x equals 0, so I can't call that a critical number. So for us, the derivative exists everywhere the function is defined. So the derivative will exist everywhere except for at x equals 0. All right, now let's locate critical numbers where the derivative equals 0. Okay, where does the derivative equal 0? Well, you can do cross products. You're going to get 0 equals the numerator. So it's always the numerator equals 0. Okay, add 6. So x equals, looks like negative 6. All right, so our only critical number occurs at negative 6. And that gives us a 0 slope. So that's our critical number there. So let's go ahead and put negative 6 in its correct location, I guess about right here. Now above that, I'm going to put a 0 because that indicates that that's our 0 slope. Okay, well, I didn't leave myself much room here, so I might want to extend that. I'm just a little afraid to. So I'll just say you might want to extend this arrow. Let's do a test with maybe negative, I'm going to just do negative 10. Let's plug negative 10 into our derivative. Negative 10 in the numerator for x would give opposite negative 10 would give 10 minus 6 a positive numerator. The denominator would be negative when I cube a negative number. So positive divided by negative is negative. So this is less than 0. So negative here. Okay, now in between negative 6 and 0, let me just choose negative 1. So f prime at negative 1. Plug in negative 1 here. That's positive 1 minus 6 is negative. Negative numerator, negative denominator, positive result. If you don't see how I'm getting these positive negative signs, pause the video. Think about you're trying out a test value. And then I'm going to plug in a positive 1 here. Positive 1 results in a negative numerator, positive denominator. I guess that would be a negative result. All right, so let's just kind of think about what we have here. The function's falling, negative rates of change. Then it has a 0 slope and changes to rising. I see that as a minimum. Then we have a vertical asymptote. On the other side of the vertical asymptote, the graph is constantly falling. This seems very interesting to me. Okay, so let's take this information here and report what we're supposed to be reporting. So the function f is increasing on the x intervals negative 6 to 0 because the f prime values are positive. I do have some negative slopes, so that must mean the function is decreasing on some intervals, and it's broken up. We'll go from negative infinity to negative 6, comma, 0 to infinity, because f prime is less than 0. All right, let's consider extrema. All right, to have a min or a max, I need to have at least a point. And notice this is a vertical asymptote, even though the slopes change from positive to negative. Okay, that doesn't mean that you're going to have an extrema, especially if this point right here is a vertical asymptote. So it's real important to investigate the behavior, where the function does not exist and what's happening. But I do notice that I do have a minimum because my graph does, my slopes do change from negative to positive here, which indicates that the function is decreasing to 0 slope and then turns around and starts to increase. So f has a relative min at x equals negative 6 because the slopes, f prime, these are the f prime values, these are going to be negative values and positive values, change from negative to positive. So that's the information that we can gain from that. I just want to mention this graph. It's a very unique looking graph. If you guys do type this into your Y1 and graph it, just notice that we do have a vertical asymptote at x equals 0, and at negative 6, that minimum is just not very obvious at all. Notice that if this is 0 right here, that the function's decreasing, and it's very obvious that the graph is decreasing from 0 to infinity. It's just right here. What's interesting is the graph is actually decreasing slowly. There's a horizontal asymptote, and it's slowly decreasing here until you get to negative 6, and you can't even see it unless you really set an incredible window. That's our minimum, and then what happens is the graph slowly comes back up. But it's real hard for us to see on the visual of the graph that there is a low spot right here as indicated by this data. So I guess you could say that this work is real beneficial in that if you just were to graph the equation in the calculator, you would clearly not see that this would be a minimum here at all. But this work verifies that there is indeed one. So I just wanted to point out that the graph is pretty interesting, and you might want to kind of look at it yourself. So see you soon.